Hey, and welcome everybody to Com42 LLM conference. Today we've got an exciting topic planned for you. And by the way, did you just see that intro right there? Yeah, the old rock star watching the World Cup. Yeah, there was no camera, no actor here, and none of that was real. Everything was AI generated. See that quality? That's a diffusion model for you, which is the entire reason why we're here for the next 40 minutes. I'm Kosseila. This is vLLM-Omni, one engine, two brands, the multimodal any-to-any inference, and let's go. Okay, so first, a very quick intro. As shown here, my name is Kosseila, founder of cloudthrill, 18 years in tech, now AI infra lead, and vLLM production stack contributor across 6 different cloud. But hey, that's not what matters. Here's the part that's actually useful to you. We have a couple of deep dive blogs, for example, like vLLM for Beginner series, if you're new into it or not, with 3 parts, starting from fundamentals to features to deployment. We also got Kiwi Cache Explainer, Explain blog to learn all about it. Then a super helpful Diffusion 101, since it's the topic of the day. Literally all the questions you never dare to ask about diffusion models, like what is diffusion, the noise and loop, diffusion solvers, CFG and negative prompts, even diffusion model papers from 2021 to 2024. The whole thing. Super simple visuals and annotation, very helpful for AI builders. And of course, no PhD required. I also happen to host a podcast called Tech Beats Unplugged. And so you can check that out for a full episode on quantization if you're into that. And that's actually about it. So we can start with the agenda. So let's do this. Okay, so what are we talking about today? Well, first we'll start with the multimodal mess and why serving text, message, video, and audio all together breaks your stack. And in section 2, we'll talk about the one engine, two brains architecture behind vLLM-Omni, where autoregressive meets diffusion across pipelines and multimodal stages and how they work. And in section 3, we'll cover the orchestration part, including the request journey and the API calls, the serving and deployment framework on a single or multi-node environment. And in section 4, we'll cover what makes vLLM-Omni very fast. I'm talking about the acceleration features with diffusion caching and parallelism dials like sequence splitting and HSPD, including quick example. We'll dive a bit deeper later on this talk. And in section 5, that's the fun part. We'll jump into a live-ish demo replay on a Nebius H100 node, testing Z image, TTS, and the brand new Cosmos 3 world model from NVIDIA, which I'm very excited about as well. And finally, we'll close on what the latest release of vLLM-Omni, the V22, shipped, and the project roadmap with more blogs and goodies. Okay, so let's start with the mess, but let me just zoom out a bit the slide back for a second, just so you guys can see the slide better. Let me switch that here. There you go. Looking better, right? Perfect. Okay. So you probably know most of these visual generation services, which are proprietary, like VO3, Kling, Midjourney, Luma, Seedance, 11 Labs for voice, and there are obviously tons more open source versions, of course. There are different models, different UIs, but one thing is common under the hood, though. They're all diffusion based. But here's the catch. They're nothing like serving LLMs. Why? Because text generation is autoregressive, so it's token by token. You cache keys and values, so it's more memory bound. And then image and video are diffusion based. So you denoise over a fixed number of steps, and every step is a full forward pass, even sometimes double, and it's more compute bound. So that's totally a different physics. So for years, if you want to text an image behind one product, you run 2 stacks, 2 engines, 2 schedulers, 2 teams to ship 1 feature. But vLLM-Omni, on the other hand, is betting on 1 sentence. What if a single engine, by the way, I was talking about the text autoregressive and image video diffusion comparison, and the way that teams are actually splitting that into stacks. And the question that vLLM-Omni is asking is, what if a single engine could serve both, actually, or even more, by the way. So let's see what this Omni engine is all about. All right, so what does Omni modality actually get you in vLLM-Omni? 2 things. One, it keeps the autoregressive support VLM is already perfect for, and extends it to anything not autoregressive like diffusion transformers and other parallel generation model, right? So on one side, we have all modalities like text, image, audio, video that can be ingested by their specific encoders. We call them modality encoders as well. And then we have the LLM AR code, which stands for autoregressive core, right? That's literally vLLM, takes care of anything LLM related. And then on the other side, we have the modality decoders or modality generators to generate all these various modality output like text, image, video, and audio. That's the any-to-any modality in and out. Again, it does that by keeping everything vLLM is great at on the AR side, the autoregressive, and grow a second brain natively for diffusion, which is exactly the picture on this slide. Now, how about the model support? How does vLLM-Omni actually do in terms of supporting all these open source models? Well, it does great, because the biggest momentum driver for vLLM-Omni is that this isn't just a paper. It's built in the open with huge OSS model support, with more than 40 architectures under one runtime, from chat models all the way to long video generations. We got the whole Qwen suite, from Qwen Image, Qwen Omni, Qwen TTS, to models like Flux, Huan, One, Stable Diffusion, Z models from GLM, and even Cosmos, the newborn model made to generate wall simulation and train robots, and the latest Helios real-time long video generation model, because the one thing you need to know is that most video gen models can only generate short clips due to their training corpus. But this one makes longer videos. And that's already 5,000 plus stars and climbing. And this list actually will definitely be different tomorrow. So whatever you're seeing here in the screen is going to be different like within weeks. But let's step back a minute and compare the AR and diffusion one more time. All right, so let me actually walk the difference between the 2 brains, right? AR and diffusion, and they're all as well. So on the left side, we have the autoregressive brain, the AR model. We can call it Talker, for example. It generates text token by token. That's your usual LLM. With pre-fill driven by KV cache, which is compute bound, and decode, that's more memory bound. The sequence length is varies per request, so it can be different. And the attention is casual, so you only look backwards to tokens. On the right side, that's diffusion. That's completely different. So the DIT, which stands for diffusion transformer brain, diffusion transformer, is more like a dreamer. So it generates pixels and waveforms by denoising like an image generation. So every single step is a full forward pass. I said also that it could be double through the transformers. Early on, it was like 50 steps. just for one image, but recently with the recent models, it's way less, up to 10, 6, or 7. So it's compute bound. And since we're not dealing with tokens, the sequence length is fixed. It's fixed by your output size. So then the attention is full. So every LLM patch sees everything, right? We also have different type of parallelism between AR and diffusion, but this will be covered later in this talk. But now look at the bottleneck though, the bottleneck row. So you have memory bound versus compute bound. That one row is why historically, as we said, you run 2 stacks, but the vLLM-Omni actually runs both brands under one runtime. And today we'll discover how. Okay, so it's always good to still check how it works at the API surface, right? Again, it's very similar to vLLM here with 2 paths under the same runtime. We have on one side the offline batch serving, which is a synchronous path called Omni. That's the main class, mostly through Python. And then we have the online serving, which is the async path or class, best for OpenAI compatible endpoint inference. But whichever door you walk through, you actually land on the same Omni stage underneath, which is known as the vLLM API. So nothing really changes here for this extension, but it's always good to know. Right, so in terms of user interface though, with vLLM-Omni, here are 3 real front ends you can try. You got first Gradio demo, that's the most basic. Then you have the Comfy UI for professional artists that can use vLLM-Omni as an endpoint, especially for a local inference. And finally, a very neat project called vLLM Playground, built by our friend Michael Yang. Shout out Michael. That now support vLLM-Omni locally through containers, one shot, or as remote endpoint, which is super cool actually, because you can launch it on your laptop on CPU and put remote vLLM-Omni base URL, and boom, you can generate pictures, or you can generate talk to speech, all those modalities just through your web UI, like Open Web UI. Or you can actually just run the REST API with the good old curl, as shown here in the command. You can see here that there's a --omni flag. That's the only thing you need to add on top of the usual vLLM serving command, which is pretty convenient. So there's no friction. There's no learning curve for vLLM users if they switch to vLLM-Omni, which is super cool. Now, let's dig deeper into the core component of the engine runtime. So first, we have the Omni router. That's the intelligence. Every request gets dispatched to the right unit by modality or by load. So for example, you ship text, that goes to the AR brain, of course. You ship video, that routes to the diffusion, right? That decision is the router's literal job. Right, and then you got the entry point. We just talked about the API layer. We got the offline API represented by Omni class, and online serving represented by async Omni class, all sitting under the same abstraction. And then you have the Omni stage. It's a sort of stage orchestrator. So anything related to the stages is managed by the Omni stage. And first of the 2 engines, as you can see here in the left side, that's the AR engine, the autoregressive engine. So all the best part of vLLM is inherited here. So no reinventing the wheel for text generation. So key cache management, page attention, continuous batching, all of those goodies, all of it comes straight from the vLLM and adapted for Omni. On the other side, you got the diffusion engine, right? And this one's native, actually. They had to come out with it from scratch. And it's also tuned by acceleration components that we'll cover later, like parallelism, etc. But under both engines, there's something called shared floor. aka the kernels with parallelisms, quantization, attention. Those are the same primitives actually for both brains, right? So AR and diffusion are benefiting from these two, from these primitives. And finally, we got the Omni connector, which is what's tying the whole thing together, like decoupling the full encode process, decode, generate, split, so like all of these stages, and transform the data from each one of them, right? This is very important to connect all these stages. So this connector is exactly where both the magic and complexity live in, which we'll see in the next slide, of course. So you can see here that AR side and the diffusion side aren't really bolted together. They're just peers. They have the same scheduler discipline, same kernel for, but different generation loop. So one is continuous batching over casual decode, and the other is a stepwise denoising. And most importantly, these modules need to exchange a bunch of key data during inference that are very important to generate whatever data or content. 3 of them are information data, so this is more like a metadata. You also have KV cache prompt embedding, that's also exchanged between these stages, and you also have latent data for encoded content, right? So those data are transferred between each one of these stages. This is a very critical piece of the architecture because all of these modules actually require a flawless interconnection. And then we actually have stages that actually talk, and how do they do that actually? So how do the stages actually talk? Well, they do that through the Omni connector. Right, so this connector splits control plane from data plane. So you got light metadata on one path, right? We talk about the information metadata, and the heavy tensors that write a separate fast path, right? And in terms of interconnect, from inside the node, it goes device to device, so D2D, GPU to GPU, so there's no host round trip. But as soon as it crosses different nodes, it falls back to device to host to device, right? D to H to D through a memory pool managed by a transfer engine like Mooncake. Most of the time is a Mooncake. And lastly, the very big difference for scaling here is that every stage replicates independently, right? So if you notice a bottleneck on a stage, you can just scale it out with which you don't need to. You don't see that in every other LLM engines, even in vLLM, right? So as opposed to the case with vLLM-Omni, you can have a stage one that is needing 4 replicas, and then another stage that needs 1, because they're completely independent. So you don't have to scale the whole pipeline. You just need to scale wherever you need, whichever stage that requires a little bit of resources. That's the advantage here. That's what makes it very differentiated compared to the other engine. And the Omni connector relies on 3 transfer engines, depending on how far the data travels, actually. So single box, that's shared memory connector over what we call the SHUM, which is the fastest one, lowest latency. Crossing nodes, that's Mooncake store connector over RDMA or TCP. And that's through the Mooncake store. So that's perfect for a high bandwidth intranode. And then you have, if you have big clusters, then you have something called the Mooncake transfer engine connector that uses RDMA exclusively, and that's built for scale, right? So you got 2 Mooncake transfer engine. One of them is mixing TCP and RDMA, and the other one is really, really made for scale. So the rule of thumb here is shared memory on one machine, Mooncake the moment you cross the network. And this swap happens in the YAML config. not the code, right? So it's very, very flexible. Now, a concrete example here with the Omni pipeline, you got, for example, one request, which is a TTS, text-to-speech ask, end-to-end. You have 3 stages. So the first one, it hits the thinker at first, then the talker, then the code-to-web. We'll cover all of these stages and their role, of course, in the next slide. But notice each arrow between these stages is an Omni connector hub, right? This is the exact example we deploy in YAML on the next slide. So keep that in mind, keep that shape in mind, thinker, talker, code-to-web. By the way, code-to-web is just, it's also called vocoder. You can also find other examples like thinker, talker, AR plus DiT. So thinker, talker is just using the Qwen Omni architecture, and then the AR plus diffusion transformer, that's with the GLM image. And then you have a very special case with a mixture of transformers that's using Bagel, where KV cache is shared between 2 generation and the understanding expert and generation expert. But this is, I would like to have just a recap just for you to take away from this, of the 3 stages and what each actually does. So the first one is a thinker. Its role is understanding. So it ingests wherever you hand it, whether it's text, image, video, audio, and produces reasoning states, what we call also text tokens or hidden state embeddings, which are handed to the talker. So this is very heavy work. And then you have the talker, which is codec logic, right? This is behind speech synthesis, for example, and it turns the thinker's text and those embeddings, codec, codes, or latent space, and the output is actually streamed down to the code-to-web. Code-to-web is just something that renders. It's just the decoding into, it's mostly a web form, so it decodes those codes into a real audible audio web form like MP3 back to the client. So these 3 independent stages or engines handle understanding, the codec, and the web form, which is responsible for the final format of the audio. Now, let's talk about deployment now. So every model has a pipeline that defines each stage. And to deploy an Omni model, you need to define those stages through a YAML deploy config. This is what we call actually placement. And each stage is actually its own engine with its own GPU budget, but you're not actually splitting one model weights across GPUs like we used to know when we deploy a model, actually. So this is not parallelism. You're just actually placing 3 engines and telling each one of them how much memory it can use and how it should run. Remember the Qwen 3 Omni TTS that we just saw a couple of slides ago, thinker, talker, code-to-web? Well, this is the YAML config, right? So let's start easy from the left side, stage 0. That's the thinker. It's pinned to GPU 0 here, and it has AI worker, right? So this is AI model. That's the LLM part, right? And it also uses 90% of the VR. That's because the understanding is heavy. You know, we have a lot of pre-fill going on here in the thinker. Then stage 1, the next stage, is the talker that takes the thinker's output and uses here 60% of the memory of another GPU, right? And right after, you got the stage 2, which is the code-to-web, the vocoder, which is the decoder that takes the latent from the talker and transforms it into an audio content. And this uses only 10% because it's not as heavy as the other stages. And the final output, of course, is the audio. But notice that here, we actually have 3 stages, 2 GPUs, but each one can scale as much as you want, right? So the fact that you have 1 GPU for a thinker and then two two stages sharing GPU doesn't mean that they cannot have each of them one GPU. It's just that you can go as far as you can, right? I know it may be confusing, but let me explain how it works, to be honest. All right, so this was actually the most confusing thing for me in this whole project, but bear with me. So two things. We have the pipeline and the deploy. And the difference is actually simple. So we got the pipeline on the left, which is written in Python. This is where the model code is, right? It defines the stages like thinker, talker, code to wave with each attributes like a class. So you do not touch this to deploy ever. And then we have the deploy YAML, right? Which is more like a recipe, config file. We also called it the placement a slide ago, right? So you can tweak the values like devices per stage, memory utilization, max sequences, etc., using the overlay pattern. So this is like a child class. So you only change whatever attribute you want, but everything else is actually default, right? And the bottom line here is a stage doesn't equal a GPU. As I said a couple of minutes ago, it's a unit of work. So it can share a GPU, as I said, like the previous two stages, or span over many, right? It's like one to many. But let's see some deployment example, though, because that's way easier than just talking about the theory. So serving a model in vLLM-Omni can be done in three ways, depending on your topology, and I would say even depending on your taste. So you can either run a one-liner, like a one command line as shown here in the first line, where you define all placement in a YAML file, right? So you put all of that in a YAML file and then pair it with the deploy --deploy config flag in your vLLM serve command with the Omni tag, right? That's all you need to do, and it's pretty useful, especially if you have a lot of attributes to change. Or in the second example, you can spread your stages on different processes or machines, right? So with one process per stage. So here, for example, you got stage 0 that will own the API server using Omni master address tag. All the other stages would just call the master as the orchestrator, right? This is like having like a database cluster where you have like one lead master and other slave databases, and this way it can span across nodes, right? So usually you use the tensor parallelism for models, but like with the vLLM-Omni, you can even split the stages across nodes, which is very, very proficient. And lastly, you can also tune per stage using the -- stage overrides, which can be super handy when you want to tweak memory utilization or anything else from the command line without editing the file and letting everything else default, for example. This way, you decide on the placement with zero change to the pipeline code. So I hope I've been clear. It's been clear enough, the difference between the pipeline and the deploy. But if actually it's not, I have maybe something else to clarify the confusion here regarding the repo structure. There was just a small change recently, for example. There has been some housekeeping lately, which can sometimes trip you up. But here's 3 things at least you need to know in terms of a repo structure. So the first YAML user templates is no longer on stage configs. It used to be in stage configs location, but it's now moved to deploy. So everything you need to define in terms of config file would be under /deploy directory, which is the new schema. Only the 1.2.2 config are in the old location. They didn't move them yet. And then the second part is the pipeline, right? So that's the code of every model. And they're split into 2. So you have on one side everything that's autoregressive and Omni related. pipelines would go under slash models, executor slash models, and anything diffusion based in terms of pipeline will go under diffusion slash model, right? And then third and last, that's more the tutorials that can be very helpful when you get started actually with vLLM-Omni. So you can find all recipes and examples like online and offline serving under recipes and example for those respectively. Okay, so before we talk about diffusion acceleration features, you should first be familiar with some diffusion fundamentals, right? I did blog about it for sure. You can see the QR code, but I actually didn't talk about diffusion much in detail. So to make it easier, I picked up 6 terms you should know in order to get going. Heads up, as I said, there's a QR code for Diffusion 101 with all you need to know in case you want to go deeper in it. But first, reverse diffusion. So training is forward diffusion. So it goes from clear picture to full noise, right? But the inference, on the other hand, is actually the reverse, hence the name. So it goes from complete noise to clear pixels, clear image, which is also called the noise in loop. And the noise in loop happen one step at a time. And next is time steps. This is just a number representation of each of the noise in steps, for example, from 1 to 50. And then comes the time step embedding. So time step embedding, this is more like a GPS signal that is generated in each step just to tell you where you at in the noising journey and what is left in terms of denoising. And then you got the denoising loop that we talked about, and then the CFG. CFG is actually a classifier-free guidance, all right? So this has 2 passes per step, so it gets a bit expensive to run. One pass is with your prompt, one is without, right? And it's usually combined with negative prompts, like saying, for example, hey, draw me a chair, but don't put a truck on top of it. I know it's weird, but this is how it works. So it adds more accuracy in terms of the image that you want to generate, but adds a little bit of latency. So there's a trade-off. And then you got a latent space, that's a VAE. They call it variational autoencoder. This is more or less like the zipper, the diffusion zipper, right? So once the noise and loop is over, VAE unzips everything back into the full resolution image or video as an output. It's like what we saw with audio, the vocoder, same thing. So it converts it into images or videos. So that's it for diffusion. Now, in terms of vLLM-Omni acceleration, we got 2 more things I would like to mention. First one is VAE parallelism, which unzips at scale, right? That decoding part can run through GPUs as well. And the second one is HSDP, which spreads your diffusion model weights across GPU or nodes. Again, this is not data pipeline, right? You're not duplicating the weights. You're just spreading evenly the weights of the model, right? So this is very different. So that's enough for now. As I said, check the QR code below. I wrote a full deep dive on diffusion models as well. But that's about it so far for diffusion. Now we're ready for the next slide. All right. Another QR code, and here we are with the whole acceleration toolbox with features like cache backend, which is my favorite. Why? Because it's a super easy win, up to 4 times speed up without changing the code. You have, for example, Tcache that caches any similar consecutive time steps. I wrote all about it in this full deep dive, so check the QR code. We also have Cache-DiT, which speeds up diffusion via DB cache. This one is very interesting because if you do video, this is your go-to acceleration because it has a lot of performance improvement for sure, better than Tcache. Tcache is mostly for images so far. And beside quantization, you got parallelism, and there's two interesting features, right? Beside the quantization parallelism, right? And these two features are Ulysses sequence parallelism, called SP as well, which splits sequences, especially when it's a 4K image, anything super big, right? Because it's very, very heavy lifting, right? So the 4K images, for example, are too big for one GPU, then it hands each GPU a slice of the pixels so it can finally generate whatever is required. And then the second one is ring attention. So it's another way to slice GPU pass data around the ring, and it stacks well with the Ulysses as well. And the last one is CPU floating of those intermediate states. Of course, CPU floating of KV cache, using solutions like LM cache, but this is more for anything that is generated between the stages. Even latent intermediate states can be offloaded to the CPU as well, which is very, very, very practical. Okay, now here's a support metric for image models where you can see every single feature. Tcache here is, for example, is actually hit or miss, but you can see all the other features like tensor parallel, sequence parallel, pipeline parallel, CFG, data parallel, etc. So it's in the repo, and you have one for image generation and every type of modality for sure. This one is, for example, video gen. You can see here that Tcache is not available for any of these recent video models, but this is more because the recent models actually didn't share something called the polynomial coefficient. I don't want to go deep into it, but it's necessary for Tcache to provide these L1 distances that are necessary to cache during the diffusion. Okay, so quick recap in terms of parallelism flags in this slide. Easy way to see this is through two families. You either split the data, talking about sequences with Ulysses sequence parallelism, or passes like CFG parallelism, or pixels through ring attention, or you can split the model like we talked about with the HSPD, right? And in this example, we can see on the left that we used HSPD to split the weights, and patch parallel to split the decoding across GPUs. Notice no CFG parallelism is used here because distilled model actually skip CFG, right? As opposed to the second example, when we can see that we have full example with CFG parallel flag split through two GPUs. And of course, you don't need a full node to use parallelism, as shown in the third example, where patch and sequence parallel is used in a smaller batch of GPUs through USB and ring attention, right? So you don't need 8 GPUs. You can also play parallelism through 1, 2, or smaller batch. One more thing I wanted to share before our demo is actually a multi-node deployment when one box is not enough, which happens more often than not. The config is still just YAML and is very simple, as shown here, with just an override that introduces mooncake connectors that build that memory pool with a master node orchestrating everything. So mooncake will wire the output from stage to stage, like stage 0 to stage 1, then over to stage 2, right? Thinker, talker, or vocoder, right? And then it does that hop by hop across machines, which is very straightforward. So this is all done through the configuration, the YAML config that we talked about, the deploy. There is no change into the code, which makes it very flexible and ubiquitous, right? This is super light. If you want to do multi across nodes communication with these stages, this happens in a YAML file, which is really, really neat. All right. Now, time for some fun, because I promised we'd have a demo, and here we are. So thanks for sticking with me. One of the models I wanted to try actually is Cosmos 3 word model by NVIDIA. This was suggested by one of the maintainers, vLLM-Omni, Roger Wang. And honestly, look at these visuals. It's so slick. I'm just going to mute it a bit, but it's really slick. So the quality is really nice. It's really neat. And so, you know, this is why, I mean, I was like, okay, let's add this test for sure. I really didn't need more convincing to try Cosmos. And a little heads up, I picked the Nebius H100 VM for the test, and you'll understand why I record the demo instead of a live, because I'm still hoping to hit a jackpot soon, but it still didn't happen. So I'm not going to let you know, a node running the whole day just for a demo. But still, you know, it's still cool, and you'll see most of it for sure. All right, let's try this out. First, I want to talk about the serve commands, because we talked about the serve-in. So we have 4 examples. I did them all, but we may not have as much time because we're almost, you know, cross the hour now. But the 4 examples that I hoped I could run will depend on the type of generation. But I'd say the one that's worth seeing is definitely Cosmos, right? Right. So you have here a Z image, you have 1.2.2 for video, and you have Quant 3 TTS, and then you have Cosmos 3. But these are the API calls that would run eventually. So all the API calls you are seeing here depend on the model that's running, be it image, video, TTS, or Cosmos. I create a menu actually script to automate the whole selection. I'll be writing a blog later and make sure to share it so you guys can reuse it right away. But hey, now let's try that Cosmos bad boy in this demo so you can see the model that's running. Let's do that. All right. So what happened here is that you can see I have 3 pans. The top shows the log. You see that the model is NVIDIA Cosmos 3. And then what happened is that I actually took a print screen, like a snapshot of a picture that NVIDIA released in Twitter. And I was like, hey, let's use that picture and try to generate a video based of it, right? So I create that script that will select whatever API call you want to do. I selected 4, which is Cosmos. So this will literally run API call directed to the server where Cosmos is running, using that picture as reference. So this will take all the attributes and arguments. You can see it in the log of the vLLM-Omni server, and it's currently generating, right? It's taking all those information and it's generating it. And if you want to see, I wanted to show you also like how the model was loaded. It was almost a no-brainer, but there was something to tweak at the end. But as you can see here, at 3:40, everything is done. The file, the video is generated. So let's see if it looks good or if it looks similar. There you go. Look at this. See this? This looks like maybe Formula 1 Grand Prix from Spa in Belgium. Super, super likely. And it has sound as well. It takes as much time for sound and no sound. And it's really, really, really realistic. So that was really neat. And it exactly the same video that NVIDIA has shared. It took 3:40. And as you can see, like the only issue I had during the deployment of Cosmos 3, even the recipe in vLLM-Omni was not really accurate. There's the guardrail that is mandatory to run with Cosmos, right? And you have to actually download it separately, accept the license. But if you want to sort of ditch the guardrails, there's no flag for it. So you got to go through that YAML file that we talked about, that deploy YAML file. So this is how I made it work so Cosmos could be serving and sort of answering whatever requests that are sent to it, right? I wish I could share more, but I'll be definitely building a blog with all those cases, all those 4 cases with the scripts and stuff to make it automated for sure. Okay, and by the way, this generation of Cosmos 3 was done through Cache-DiT, and within this generation, when using Cache-DiT, I had 4 times faster generation thanks to this caching. This example is on 1.2, but I had similar performance also on Cosmos. So Cache-DiT is really the go-to acceleration for video. And one thing I wanted to add actually before wrapping up is like real quick before we move to the roadmap is I wanted to mention 2 very interesting features for text-to-speech and Omni models. So vLLM-Omni now supports async chunk and audio streaming output. This is really increasing the throughput and improve the latency, making it feel more real conversational, as you don't have to wait for the full answer, right? So each Stalker's chunk is streamed as soon as it comes out. And as you can see in the next benchmark, so it yields a 12 times faster time to first audio packet. We call it TTFP because it's time to first packet, audio packet. It's because it's no longer token anymore here. We're not talking about token, but about packets. And it holds under load with over 8 times speed up and 10 times concurrency. And also notice the new metric called RTF, which is a real-time factor. That's more like a realistic feel metric of the dialogue. And the lower it gets, the better. And of course, with batching, we can scale throughput up to 4 times higher than HF transformers, even more actually. I've seen batches of 7 in the latest release. So yeah, I just wanted to add this one because it feels like an orphan one, but let's get to, here we are, ready for the final recap. That's the home one actually. So let's take this baby home with the latest updates from vLLM-Omni and more importantly, where it's going. So just with this week's last release, the V22, there's already a lot to unpack with features like day 0 support for NVIDIA Cosmos 3, world model, like we just saw in the demo. They also added robo-serving integration with models like 𝐉𝐨𝐢𝐧 and OpenPy with real-time serving API. We also saw production TTS and Omni performance improvement in high concurrency across Qwen 3 and Vox CPM2. Plus faster diffusion on video models like Wan, Hunyuan with diffusion caching and parallelism we talked about already, and a broader quantization, obviously, from FP8 to FP4. And obviously, vLLM-Omni team is still cooking. They're relentless and just getting started, actually, in terms of roadmap with plans for more diffusion backends, diffusion continuous batching, video streaming output on top of the audio streaming output that we just saw, and also an engine integration of the new model runner V2 and a deeper disaggregation with Omni connector and Omni router across clusters. And finally, even reinforcement learning integration with a new project called the vRL-Omni, which is a new RL post-training for generative models where vLLM-Omni is actually used as called here the rollout engine, right? So that's even in training, post-training, vLLM-Omni is going to be used as a rollout model, and I'm going to actually call it viral Omni, to be honest, at this point. Because crazy to see a project growing so fast when we know that the first social media launch was last December, and I remember it. And now they reached more than 5,000 star in GitHub which is really, really impressive in just a few months, because it's actually all built in the open. It's really, really impressive momentum, which is why I picked this topic. To be honest, it took me a lot of time to prepare this slide, but I'm happy I got to share it with the community. You, of course, can join their Slack for sure, and you can just start the GitHub. So go do that. Just scan the code right there, and then you can join and learn. And they also have a Slack channel. They're very helpful, and it really, really is buzzing right now. All right. So this is it. And if you want to go deeper, let me zoom out, maybe zoom in a bit. There you go. So this is it. If you want to go deeper, check out these deep dives blogs. You can find them all on cloudthrill.ca/blog. There's also a newsletter. And if you have any question, just hit Kosseila HD on LinkedIn, and that's where to find me. So that was vLLM-Omni, one engine, two brains, any-to-any inference. And that's it, everybody. Thank you for your time, and